The double transpose property. Hello everyone. To begin, let's quickly recap what we covered in the previous subsection. We learned that the transpose of a matrix is a straightforward operation obtained by simply interchanging its rows and columns. Now, we are going to build upon that knowledge by introducing the double transpose property. This is a fundamental algebraic rule that describes exactly what happens to a matrix when this transpose operation is applied twice to the same matrix. Over the next few slides, we will explore how this works and why it is such a useful property to understand. Understanding the concept. Now that we have a clear understanding of what a single transpose is, let's move on to the core concept of this lesson. The double transpose property states that if a matrix is transposed twice, it returns to its original form. To put this in simpler terms, you can think of the second transpose as an operation that effectively undoes the first one, bringing the matrix back to its starting state. If we look at the formal mathematical statement for any matrix A, this relationship is expressed as the transpose of A equals A. I should also mention a quick note on notation, as different textbooks use different symbols. While we are using a prime symbol here, some of your materials might use a capital T superscript to denote a transpose. In those cases, the property is written as the transpose of A equals A. In the next slide, we will break down the logic of why this happens step by step. Step-by-step logical breakdown. Now that we have established the formal definition of the double transpose property, let us examine the underlying logic to understand why this property holds true. We can break this process down into two distinct steps. First, let us look at step 1, the first transpose. When we find the transpose of matrix A, which we denote as a prime, we are essentially rearranging its structure. Specifically, we convert row 1 of matrix A into column 1 of a prime, and row 2 of matrix A into column 2 of a prime, continuing this pattern for all subsequent rows. Now we move to step 2, the second transpose. In this step, we take the resulting matrix, a prime, and apply the transpose operation to it once more. This means we convert row 1 of a prime into column 1 of a prime prime, and row 2 of a prime into column 2 of a prime prime. To put this into perspective, since the rows of a prime were originally the columns of matrix A, converting them back into columns simply restores the matrix to its original configuration. This logical loop is what ensures that the second transpose effectively undoes the first one, bringing us back to our original matrix. Real-world analogy. Think of the transpose operation as being similar to flipping a piece of paper over. If you flip the paper over once, you are no longer looking at the front. Instead, you are looking at the back side. In our lesson, this represents the first transpose of the matrix. However, if you flip that same piece of paper a second time in the same manner, you will find yourself looking at the front side once again. This mirrors the double transpose property, where the second operation effectively undoes the first, returning the matrix to its original form. Now that we have examined the logical breakdown of how rows and columns are interchanged, let us use a real-world analogy to make this concept more intuitive. With this conceptual understanding in place, let us move forward to the next slide, where we will apply this logic to a detailed numerical example. Detailed example. Now that we have discussed the theoretical concept and the analogy of flipping a piece of paper, let us put this into practice with a concrete example to see the double transpose property in action. Let us consider a matrix, which we will call matrix A. This is a 3x2 matrix, meaning it consists of 3 rows and 2 columns. The elements are as follows. The first row contains 5 and 8, the second row contains 2 and 0, and the third row contains -1 and 4. We will begin with step 1, finding the first transpose, denoted as a prime. To do this, we interchange the rows and columns of matrix A because we are switching the dimensions. Our 3x2 matrix will now become a 2x3 matrix. Specifically, the first row, 5 and 8, becomes the first column. The second row, 2 and 0, becomes the second column, and the third row, -1 and 4, becomes the third column. This results in matrix A prime, where the first row is 5, 2, -1, and the second row is 8, 0, 4. Now we move to step 2, finding the transpose of a prime, which is written as the transpose of a prime. Once again, we interchange the rows and columns. This time, our 2x3 matrix will return to being a 3x2 matrix. The first row of a prime, 5, 2, -1, becomes the first column. The second row, 8, 0, 4, becomes the second column. As you can see, the resulting matrix consists of 5 and 8 in the first row, 2 and 0 in the second row, and -1 and 4 in the third row. To conclude, if we compare this final result with our original matrix A, we find that they are exactly the same. This demonstrates that the transpose of a prime equals A. This confirms the property we discussed earlier, that applying the transpose operation twice restores the matrix to its original form. Key takeaways. Now that we have walked through the detailed example, let us summarize the key takeaways to ensure you have a firm grasp of the double transpose property. First, let's discuss the inverse nature of this operation. In mathematics, when we say the transpose operation is its own inverse, we mean that applying the operation a second time completely reverses the effect of the first one, bringing us right back to where we started. Secondly, consider the restoration of dimensions. If we begin with a matrix A of order m by n, the first transpose, a transpose, flips those dimensions to n by m. However, when we perform the second transpose, the transpose of a transpose, the dimensions are flipped once more, returning the matrix to its original order of m by n. Finally, it is important to recognize this as a universal identity. The property that the transpose of a transpose equals A holds true for any matrix you encounter, regardless of whether it is a square matrix or a rectangular matrix. While this property is logically straightforward, there are a few common pitfalls that students often encounter, which we will address in the final slide. Common mistakes. First, it is very common for students to confuse the transpose of a matrix, denoted as a prime, with the matrix inverse, denoted as a inverse. You might be confused because the inverse of an inverse also returns the original matrix A, which looks very similar to the property we just studied. However, please remember that these are two entirely different operations. As we saw in our previous slides, finding a transpose is a simple matter of interchanging rows and columns, whereas finding an inverse is a much more complex algebraic process. Secondly, be mindful of calculation errors during the first step. Since the second transpose is performed on the result of the first, any mistake made while creating a prime will be mirrored in the second step. This will lead you to a final result that does not match your original matrix A, which might make you think the property itself is wrong. To prevent this, I highly recommend that you always double-check your first transposition before proceeding to the second one. Now that we have covered the theory and a practical example, let us conclude by discussing some common mistakes to avoid so that you can apply the double transpose property accurately.